Hi, and welcome to Geology. Today we are going to start talking about plate tectonics and how the different ways in which the Earth is moving causes different types of reactions. And so as we kind of move through this unit, we've already kind of gone through the layers of the Earth. So I want to take a few minutes and kind of just revisit the lithosphere, the ozonosphere, the mesosphere, outer and inner core. Remember that they go in alternating layers, is that we have our ozonosphere as our crust. The lithosphere is our it's magma or melted rock almost that is actually convecting. And this is where we're going to focus in on a lot, because this convection in the ozonosphere is what causes plate tectonics. And then finally, as we move down into the mesosphere in the outer core and the inner core, we also have in that outer core another convection cycle, which creates our magnetic field, which then plays a effect also on the ozonosphere and lithosphere. And so these convection currents are kind of the key to things that we're going to talk about the next couple of days as we move through our different boundaries and everything. So do grab a sheet of paper and a pencil as we take some notes today and kind of talk about some of the foundational parts of tectonic movement. So the first thing we want to discuss is the theory of continental drift. And so this is still a theory. There are a lot of things that have come into play, especially as technology has become more advanced, and we will definitely talk a lot about this. But just in general, the theory of continental drift is what we call a theory that the plates have shifted from one spot to the next. And a gentleman named Alfred Wegener came up with this hypothesis, and he thought that continents once formed a single landmass, which we call a supercontinent, Pangaea, and over time they started to break up and drift apart. And so we are going to talk about what are these pieces of evidence that we can use to help support the idea of continental drift and how the continents are actually moving. Now, I'm a firm believer with technologies, we have satellite images and everything, is that we can actually measure the distance of how they are moving currently as to previously when Alfred Wegener was proposing this idea. They didn't have that technology. So they had to rely on these four pieces of evidence that we're going to discuss right here, which is fossil evidence, evidence of rock formation, climatic evidence, and missing mechanisms. But now, as geologists, we can actually measure the plates' movements as well as even know how fast they're going to change in that rate, and we'll talk about that even more. So those first four pieces of evidence, though, are things that we can still use to show that at one point some of the continents were a lot closer to each other than they were previously. And one of the biggest pieces of that is fossil evidence, where a fossil can be found in one area and then possibly somewhere else. So a great example of that is our index fossils that we talked about previously in our last unit, is that we can look and see that this one fossil is found here in Kentucky, let's say a trilobite. It can also be found actually in Europe. And so the idea is that, well, if it was here, how did it travel all the way to Europe too? So the part of that is the idea that maybe they were closer together. Same thing with definitely different types of mammoth, woolly mammoth are a great example, and also Tyrannosaurus rex is a great example. Not the best swimmer, if you could imagine, but he has fossils, Tyrannosaurus rex does, on both Africa and South America. So once again, T-Rex didn't fly, nor did he swim very well. So there's no way we could possibly think him traveling across the Atlantic Ocean. So that evidence suggests that possibly those two plates were at one point much closer together. Another great example of continental theory is rock formations, meaning that we can look at one area and say, like, these rocks were formed during this period of time and use those as evidence for other areas. The Smoky Mountains or the Appalachian Mountains are a great example of this. So evidence of rock formations suggests that areas along the coast of one continent match the coast of another. And so once again, the Appalachian Mountains or our Smoky Mountains is a great example because we can actually see parts of them come back up through Europe, and meaning that same rock configuration, the way that they have been solidified, and then how they've been put into a certain position or deposited, and then even having the same fossils within them. So it highly suggests that more than likely these mountains are of the same chain, but there's a big ocean in between both of them. So what happened? And so that's another example. Climatic evidence is a great example of that. We can look at glacier periods and see that that they've all been eroded during a same time period. And then finally, that missing mechanism, or that missing piece that Wagner always needed. So what was that piece? And now, like I said, we kind of have it with that technology aspect of it and knowing how fast the plates are moving. So many scientists rejected Wagner's hypothesis because it was hard to believe that the large landmass could plow through an ocean. But now we know that happens. We have satellite images of the ocean floor. We understand with our law of superposition how things work, and then even with our absolute age, by figuring out exact age of radioactive decayed elements, we can look at many different things and really contribute to the idea that more than likely these plates possibly were once much closer together. And we'll even show evidence of how we know some of the plates are going to start breaking apart differently as we move forward in this unit too. So one of the big things that we're going to talk about is the mid-oceanic ridge. And we're going to spend a little bit of time here the next couple of days as we kind of talk about Iceland, because Iceland is a perfect example of things that are happening in the Atlantic Ocean. So the mid-oceanic ridge is a huge discovery that it's a huge crack that runs down the Atlantic Ocean. So in between the United States and Europe and Africa and South America. So in 1947, scientists set out to map the ocean floor, and they did this. So once again, 1947, technology is not where it is today by any means. So how they did this is that they would get in a boat and drop a really long rope down until it hit the bottom of the ocean floor, measure that, drive a little bit further away, drop the rope again. And they kept getting different types of depths, and that was helping them figure out a couple of different things. The significance of this is that they actually found a couple of pieces of information that were highly, highly important. So the first one is that sediments that cover the sea is thinner closer to the ridge, meaning that as they got closer to this ocean ridge that was there, they noticed that the sediment was thinner. And that's because there is a crack there that is creating new crust. So by the mid-oceanic ridge, new crust is being created. So remember, we talked about igneous rock is going to be what is making the rock surrounding the mid-oceanic ridge. So there is a crack in the lithosphere that is exposing the asthenosphere, and as it does that, it allows some of that magma to come up to solidify and create new rock. So in the mid-oceanic ridge, new rock is being created. And so they were also then able to say ocean floor is very young, meaning that as new rock is being created and pushed out of the ridge, it's then pushing other rocks and continents further and further away. So ocean floor is very young, whereas our continental crust has been eroded and through all different types of processes. So those are normally much older. And so then we are able to look at that and radiometric date it and see that the seafloor closest to the ridge is younger than the counterparts further away. So meaning closer to the ridge, and I'm going to show you an example here. So here's our mid-oceanic ridge here in the blue. And so let's say that this was 25 million years ago. This is when the ridge just first started to split apart. So we have our asthenosphere here, our lithosphere here, and so that convection rises up and pushes this plate this way and pushes this plate this way. So imagine it like almost like a conveyor belt. So force, push this way, force, push this way, and over time that new crust spread further and further out. So it pushed the continents further and further away. So new crust is being created here. So younger crust is being represented by the blue, and it's pushing that older crust further and further away. So that is what we call seafloor spreading. And Harry Hess is the one who actually suggested this, that the center of the ridge had a big crack in it, and the magma would rise and cool and solidify, making new crust by that mid-oceanic ridge. And so this crack actually runs all along the Earth, and we'll talk more about it, but it's mostly going to focus in at that Atlantic portion, the Atlantic Ocean, where we can really get some good evidence there. So one really interesting thing that helped us figure all of this seafloor spreading and continental drift out is what we call magnetic reversal. And what this represents is that in magma, it does have an abundance of the element iron. And you might remember we talked about this at the beginning of the year. This iron is really significant because it is, once again, magnetic, and we're able to use how that magnet works to kind of figure out where the ages of the rocks are. So magnetic strips on the seafloor actually are going to mimic and lay and solidify the way that our compasses would, meaning that if right now, when it's happening at the bottom of the ocean floor at the mid-oceanic ridge, as the magma comes up and it cools off, those iron particles, the iron is the northern pole of the iron is going to point north, just like our compass would. And so as we observe it, we could take a compass to that and see that magnetic, that those iron particles pointing north. On the ocean floor, the iron particles will cool, and that's what this is kind of saying here. On the ocean floor, the iron particles will cool, lava will align with the current pole. And so this reversal process actually happens, which is paleomagnetism. Lava or other rocks form, they can capture a remnant of the magnetic field direction. And so meaning that over time it kind of flips back and forth. And so scientists were really puzzled, why do some of the strips of magnetic or the iron particles on the seafloor point north, and why do some of it point south? And that is because the scientists have been able to come up with the idea of our magnetic reversal, meaning that the convection has flipped over and over and over again. So paleomagnetism, lava or rock they capture a remnant of the magnetic field direction, creates bands of rock with alternating magnetic alignment, and it can flip back and forth, back and forth, back and forth. And so that last part is matching the magnetic pattern. Scientists were able to assign the seafloor rock age. And as they did that, we're then able to kind of look at what is actually happening with this magnetic reversal and why does everything flip. So we're going to continue to talk about this more, but make sure you get this down in your notes, and we'll continue our discussion about magnetic reversal next.